In the previous tutorial on using AutoGluon for image data, we saw that deep learning involves tons of design decisions, we call these hyperparameters, that affect the performance of the resulting model. Some common hyperparameters include choices around network architecture, such as how many layers should my network have, how many weights in each fully connected layer, how many filters in each convolutional layer, and of what size. Should we add residual connections, what activation function should we use, etc., etc. Furthermore, around the optimization of the network parameters, there's also many hyperparameters that need to be chosen. For example, which optimization algorithm to use, what learning rate to use for this optimization algorithm, how to set a dynamic learning rate schedule, and so on. Additionally, we might want to regularize our network to avoid overfitting. Here we encounter questions such as, to what degree should we use the following regularizers, including dropout, weight decay, things like batch normalization, and others. Furthermore, we have questions around transfer learning. Should we initialize our network from a pre-trained model, and if so, which one should we be using? Finally, there may also be questions regarding data augmentation, such as, should we augment our training data with synthetically generated examples? And if so, which augmentation technique should we use? There's now, at least 20 or 30 augmentation techniques that have become popular for image data because it's pretty easy to think of reasonable transformations of image data which should not change the underlying label. This tutorial will help you handle these issues. Unlike the models we previously saw for tabular data, for which reasonable default hyperparameters were existing that we could get pretty good performance with, the complex neural networks used for image data and also those for text data are often limited to suboptimal accuracy unless their hyperparameters are appropriately chosen. Because it's usually unclear what hyperparameter choices will be good for a particular dataset, deep learning has sometimes been referred to or cursed as dark magic or alchemy. There's also a joke about grad student descent, which evokes the idea of a deep learning PhD student blindly tweaking things in an effort to make progress. To address this issue, AutoGluon trains many networks automatically with different hyperparameter choices for each. Instead of having to know what specific hyperparameter values to use, you can instead specify a search space of many hyperparameters to consider, and also specify how to search through this hyperparameter space for the best configuration. If these are properly specified, you may be able to achieve superior accuracy within less training time, but even using AutoGluon's default hyperparameter search space and search strategy should allow you to achieve reasonable accuracy if you let fit run long enough with many trials. In this tutorial, we'll work with the same image classification data as before from ShopEIET. Recall that fit partitions the provided data into training and validation sets automatically. Instead of the defaults, here we'll show how to specify which pre-trained neural network candidates AutoGluon should consider during fit. Given such a list, AutoGluon will try transfer learning from the different networks in this list to identify the best performing candidate. In this example here, we consider two candidate pre-trained networks, ResNet 18 and MobileNet v2. Here we define this as a categorical search space, meaning a search space of discrete options to select from. In this example, the MobileNet has a multiplier parameter, which itself we decide should be a searchable hyperparameter. Also a categorical search space here, containing the options 0.25, 0.5, or 1. In this case, the multiplier parameter controls the width of the MobileNet's layers. Beyond specifying the space of hyperparameter configurations to consider, you can also tell AutoGluon what strategy it should employ to actually search through this space via the AutoGluon searcher object. AutoGluon supports various search strategies to seek out the best hyperparameter values. This process of finding good hyperparameters given a search space from a given search space is commonly referred to as Hyperparameter Optimization or Hyperparameter Tuning. After the searcher has specified which hyperparameter configurations to try next, AutoGluon relies on a scheduler to actually launch and orchestrate training jobs under these hyperparameter settings. First in, first out scheduling simply runs training jobs in the order that hyperparameter configurations are suggested by the searcher. If a training job does not require all the available compute resources, the scheduler may launch other jobs in parallel while sufficient compute resources remain available. A straightforward hyperparameter optimization strategy is to simply use this first in, first out scheduler with a random searcher that simply suggests random hyperparameter configurations from the search space. This seems very naive, but random search can be surprisingly competitive in practice and is much better than grid search for optimizing over many hyperparameters simultaneously. Bayesian optimization is a technique that uses previously tried hyperparameter configuration, validation, and resulting validation performance observations to learn something about which hyperparameter configurations might be promising in the future. From a set of previously tried hyperparameter configuration, validation performance pairs, Bayesian optimization fits a probabilistic model to these pairs called the surrogate model to actually estimate the underlying function that maps hyperparameter configurations to the validation performance of a model trained under this hyperparameter configuration. It then uses the probabilistic posterior estimates of the surrogate function to decide which hyperparameter configuration to try in the next training job. Here we follow an acquisition function that controls whether we prefer to try a configuration we're confident should perform well or a configuration whose performance we're highly uncertain about. Note that we really have to do both in order to gradually converge upon the best possible hyperparameter configurations. This is known as the exploration-exploitation trade-off. After a new training job completes under a suggested hyperparameter configuration, we use the resulting performance produced by this hyperparameter configuration to update our surrogate model, and we keep iterating this process. The link above provides a nice interactive tool to get some intuition for Bayesian optimization. So here, suppose we have one hyperparameter on the x-axis, and the y-axis pretend up here shows the validation performance of our resulting models trained under this hyperparameter. Here, pretend the purple function represents the ground truth performance that will be achieved under each hyperparameter configuration, so that 5 would actually be the best possible hyperparameter for configuration that leads to the maximal validation accuracy, say. Here in gray and black, we show the probabilistic surrogate model that we have fit to the data so far. In black, the estimated function. In gray, our uncertainty about this estimated function. Suppose for now we've only so far tried training the hyperparameter configuration shown here, say 0.5 about, and this was the resulting performance we saw. Which hyperparameter configuration should we try next? Bayesian optimization uses this acquisition function shown in green to decide this. The acquisition function should ideally trade off between configurations we're uncertain about and configurations we think are promising. So here in the first step, the acquisition function told us to try the hyperparameter near 1 first. And so we try that value and say it ended up performing this well. Then we use that information to update our surrogate model. And again, we'll now have a new acquisition function corresponding to the new surrogate model, which will tell us which hyperparameter configuration to try next. In this case, say it's this red point. Now that we've tried this hyperparameter configuration and seen that it actually performs worse than the previously tried hyperparameter configuration, the resulting update to our surrogate model suddenly makes us realize that we're very uncertain about the performance for large hyperparameter values since we've only tried small ones. So now the acquisition function tells us to try the largest possible hyperparameter value. So now we go and try that one, and so on and so forth. We keep following the acquisition function, trying the hyperparameters it suggests, and recording their resulting performance and updating our probabilistic surrogate model. And you can see that by following this process, we pretty much converge upon the global optimum here. And there's very little uncertainty left in the function at the good regions of this hyperparameter space. Similarly, we can construct another search space to identify what optimization hyperparameters work best for our task. Here we demonstrate this for the Nesterov Accelerated Stochastic Gradient Descent Optimizer, specifying a real search space that instruct AutoGluon to search within continuous valued ranges, optionally on a log scale shown here. Note that you can use analogous AutoGluon code to search the hyperparameters, here constructor arguments, of any Python object that gets passed into the training function. Here we show how you can use Bayesian optimization for hyperparameter tuning inside of AutoGluon's fit. In this case, we'll use the AutoGluon SKOpt searcher, which uses a Bayesian optimization implementation implemented from the scikit optimized Python library. Here, just for fun, we'll perform Bayesian optimization using a random forest surrogate model with acquisitions based on the expected improvement acquisition function. Here we can specify the search strategy as a fit argument. SKOpt here stands for scikit optimizes Bayesian optimization implementation. And we can specify various search options for this Bayesian optimization, including the base estimator, i.e. the surrogate model, as a random forest, and the acquisition function as the expected improvement. Note that in this demo, we're using a really short number of training epochs and a really small number of total HPO trials just to make sure things run quickly. You should really set these to larger values in practice and just to get a better sense of how these things actually work out. So once we've specified these things and we call fit, it'll start launching training jobs under various hyperparameters suggested by the Bayesian optimization. Here, recall again that we had decided our hyperparameters included the choice of pre-trained model. It could be either the ResNet 18 or the MobileNet with certain hyperparameters of its own, as well as the choice of optimizer. Because the optimizer itself has hyperparameters, here the optimizer is an object that we can't print out its hyperparameters in this Python dictionary easily. But here you can see, for example, in the first training job that we will be trying the ResNet 18 as our pre-trained network to fine-tune. Here we also called fit with a verbose flag, so it'll print a lot more output, such as what these actual networks look like. And you can see they're pretty large. Just printing out their architectures takes quite a while. And so, yes, it'll, just as before, it'll specify running different training jobs under different hyperparameter configurations. And then at the very end, it'll run one final fit on the merged training and validation data with the best hyperparameter configuration that it found. Here we can see the performance, the course of training essentially, in each individual trial of HPO. Again, we're just running 2 epochs here, so it's hard to discern many trends beyond that things tend to improve in the first 2 epochs. Finally, we can see the best validation accuracy achieved was 0.4, or 40%. We can evaluate the resulting model on our small test data set once again, just as before, and we see that it has an accuracy of 50%. In standard Bayesian optimization, we wait until a training job completes to see what validation performance of the corresponding fully trained network is, and then we decide what hyperparameter values to train next. We can also measure the validation performance, however, of the network after each epoch within a training job, as we just saw in the previous plot. If a network displays poor performance in the first few epochs, this is probably not a promising hyperparameter configuration to explore further, or a network that's worth spending a lot more compute training. Instead, this training job may be preemptively terminated early to free up compute resources to start training a different network with different hyperparameters. This kind of strategy is known as Hyperband in the literature, and here's how you can use it in AutoGluon. In the context of image classification specifically, all we have to do is call fit once again and just specify that our search strategy is now Hyperband, say, instead of the SKOpt searcher. And Hyperband has its own options you can set. These are optional, so you don't need to set them unless you know what you're doing. We can then run the resulting fit, and after a long time. So here we actually run things for a longer number of epochs to show the benefits of this early stopping strategy. And we show a much larger number of trials to really show you that some trials get stopped early while others are allowed to train fully. And so this will take you a lot longer to run on your machine. But the end result looks something like this. You can see here that some of these trials that tended to perform much worse than other trials were early stopped right away at epoch number 2 already, or epoch number 3 technically, starting at 0, because these trials there was already trials that were performing much better by the time they hit epoch number 2. We can see that the resulting accuracy on the validation data of the best model found during this hyperparameter search is 80%. Hyperband uses random sampling to propose configurations and successive halving to prune them early on in the training process. Successive halving basically just terminates the worst bottom half of the current training jobs every few epochs. However, this may be way too aggressive. Some hyperparameter configurations that are actually good, meaning they would at the end of training display good performance, might just happen to exhibit poor performance at an early or certain training stage. For example, things like dropout or using a small learning rate tend to require more training in order to actually get the same quality of performance. But then if you keep training longer, actually these kinds of networks may get better performance than their counterparts that are not using this same dropout, say. To avoid being guaranteed to kill all these good hyperparameter configurations due to this early termination, we instead run numerous successive halving brackets in Hyperband where random networks in every bracket are allowed to train for all epochs. And an increasing number of the networks in each bracket are actually allowed to train for all epochs. So here we show 4 different brackets of Hyperband. In the first one, we're pretty aggressive, and we kill many, many of the training jobs early on. But we allow only the ones that even in early stages already displayed good performance to fully train. However, in subsequent brackets, we are less conservative now, and we allow more of these networks to fully train. For example, in the final bracket here, we let all the networks that remain fully train. We can evaluate the model we just produced from our Hyperband search on the test data, just as before, and we see that it achieves almost 90% accuracy. As next steps, we recommend you try playing with AutoGluon's various searchers and schedulers to see how they affect the resulting image classification accuracy. Make sure to increase the number of epochs and the number of hyperparameter optimization trials to actually get a realistic picture of the behavior. For large-scale hyperparameter tuning, you can actually use AutoGluon to easily distribute these hyperparameter optimization jobs over multiple machines by clicking on the following link here, which will take you to a tutorial. Here's some references if you're interested in learning more about hyperparameter optimization.